For decades, backpropagation has been the backbone of deep learning. However, backprop requires full forward passes, full backward passes, stored activations, and strict sequential dependencies across layers. So this is where NoProp comes in. NoProp, short for no propagation, proposes a new way to train neural networks. Instead of sending information forward and errors backward to the entire network, each block learns locally, almost independently. The key idea comes from diffusion models. In diffusion, instead of predicting an output in one shot, you start from noise and iteratively denoise toward a target. NoProp borrows this idea but applies it to classification. And here's how it works. During training, each block receives two things: the input image and a noisy version of the label embedding. The block's job is simple. Denoise the label slightly, that's it. There's no global forward pass, no error signal flowing backward. At inference time, things flip. You start with pure noise in label space, and each block takes that noisy label, nudges it closer to what it thinks the correct label should be, and passes it on. After several steps, the final representation lands close to the correct class embedding. So next we will move into the mathematical core of this NoProp optimization method. So here this is the update rule, and here we have the neural block. This is the only learned part of the dynamics. Each block takes the current noisy label state ZT-1 and the input X and predicts where the label should move next. That's it. And it is not creating a feature hierarchy. And we also have this skip connection, like it is simply taking the previous state unchanged, scale it by BT and adds it. And this is used to stabilize dynamics. And also we have a stochastic term, and it fulfills two roles. It enforces the diffusion interpretation, like the model must learn to denoise under uncertainty. This noise term is derived from a normal distribution, and it prevents blocks from overfitting to a deterministic trajectory. It should be stochastic. And we also have this loss function. Though it looks a little bit terrible and complex, it is really simple. And we have the classification error. This is the only global supervision signal. And we also have the prior regularization term. It ensures that the starting point Z0 truly behaves like noise. We also have the local denoising loss. Each block is trained to map a noisy label representation directly toward the true class embedding U of Y. And the weighting SNR, or signal to noise ratio T minus the differences between two time steps, ensures that early steps focus on cause correlations and later steps focus on fine refinement.